Shall we start?
Okay.
Okay, ma'am. A very warm good morning to one and all. I am Mathew, Department of Applied Science and Humanities of Universal Engineering College, Valivattam, invites you to the second day of our 5-day faculty development program on discrete mathematics, graph theory, and its applications. Thank you all for joining us for today's session. Today's topic is Combinatorics, which is presented by Dr. Lisa Mathew. And Dr. Lisa Mathew is working as a professor, head of department of basic science in Amal Jyoti College of Engineering, Kanirapalli, Kottayam. She has obtained PhD, MPhil, and MSc from Madras University. She has published 10 journals and attended 20 seminars and conferences. She has served in many engineering colleges in Kerala and has worked as research fellow in projects sponsored by Fujitsu Laboratories Limited, Indo-French Center for the Promotion of Advanced Research and Board of Research in Nuclear Sciences. Now, I would like to invite Mr. Rahul Ravi, one of the coordinator of our 5-day FDP. Please, sir.
Good morning all. The second day of our FDP is going to start. For handling today's session, I invite Dr. Lisa Mathew, the HOD of Amal Jyoti College of Engineering, Kanirapalli, and she's dealing with the topics combinatories. Combinatory is the main part of the discrete mathematics. I wish that today's session is with great experience to all of you. Thank you. I welcome to Lisa ma'am for our college. Thank you, ma'am.
Thank you, sir. First of all, I'd like to thank the organizers for inviting me as a invited speaker for this session. Actually, I understand that at least around half the participants in this webinar are students. So I have intended it. My talk will be level mainly for the students. Of course, I will be talking about a few applications a little later. But I made it a little simple because I thought the students will not be able to understand if I go at a very high level. So I hope the rest of you understand. Okay, now let me start my talk. First of all, this is an overview of what I'm going to do. We'll look at that later. Now, what is combinatorics? Combinatorics or combinatorial theory is a major mathematics branch. It has extensive applications in many fields such as engineering, for instance. Image analysis and communication networks. In computer science, we have computer and natural languages, graphs, and intelligent computing. It has applications in natural and social sciences, biomedicine and molecular biology, operations research. Under operations research, we have transportation and scheduling, and it also has applications in business. Now, the usual scenario is that many real-world problems are mathematically intractable or very difficult to solve. So, in these cases, we can use combinatoric techniques to count, enumerate, or represent possible solutions in the process of solving application problems. Generation of combinatorial sequences such as permutations and combinations have been studied extensively because of the fundamental nature and the importance in practical applications. So as I said earlier, combinatorics is a branch of pure maths concerning the study of discrete and usually finite objects. In other words, it is a science of counting. It deals mostly with determining the number of different possibilities arising in different situations. Now, counting is something that all of us are familiar with. In fact, there's archaeological evidence that humans have been counting for at least 50,000 years. Now, every child, when he first goes to LKG or nursery, one of the first things he learns is, along with his whichever language he is learning, be it English or Malayalam or whatever. The one thing common that every child learns when he first starts his schooling is how to count. 1, 2, 3.
Excuse me, ma'am.
Yes.
Can you speak without your headset? There is some audio disturbances.
Right. Can you hear me? Can you hear me now?
Yes, ma'am. Okay.
Okay.
Okay, ma'am.
Now, as I said earlier, one of the first things that every child learns to do when they start their formal education is to learn to count. But then after some time, we move on to what are called more difficult areas. Even in mathematics, we uh, we do very little of actual counting, and then we go to things like geometry, algebra, things like that. I'm not saying that those are not important, but then counting is much more than what we normally think it is. So, although we do not consciously solve combinatorial problems, we use these arguments in many situations of everyday life. For example, if I have a game, football game, for instance, I'd like to count the number of games N teams would play if each team had to play all the other teams exactly once. That is a combinatorial argument, finding that out. Or when I played game chance, such as cards, or even board games, like most of you would have played either Ludo or Snake and Ladders as children. And the next one is solving a Sudoku. Okay, now where did this all originate? Most, as far as I found, most of it originated in our own India. Okay, the first mention of a combinatorics problem occurs in the Bhagavad Sutra. The problem was how many possible combinations of tastes were possible when selecting tastes in groups of ones, twos, threes, etc. from a selection of 6 different tastes. In the 2nd century BC, Pingala included an enumeration problem in the Chanda Sutra, which asks how many different ways a 6-syllable meter could be made from short and long notes. This is the mathematician and sage Pingala. A number of meters which had n long notes and k short notes, and this is equal to our modern binomial coefficients. The ideas of the Bhagavad Sutra were generalized by the Indian mathematician Mahavira in 850 AD. Pingala's work 1100 AD. Bhaskara was the first known person to find the generalized choice function. Now, the choice function is the equivalent of our binomial coefficient. Although there are evidences that Brahmagupta may have known it earlier. And Hemachandra asked how many meters existed of a certain length if a long note was considered to be twice as long as a short note. And we find that that is equal to our modern Fibonacci numbers. Now, apart from India, in China, the Chinese solved what is called the Lo-Shu square, which is the combinatorial design problem of the normal matrix square of order 3. Now, this is the Lo-Shu square. And then the Persians took the binomial coefficients discovered by the Indians and used it for polynomial expansion. Then, apart from Asia, in Israel, the philosopher and astronomer Rabbi Abraham ibn Ezra established the symmetry of the binomial coefficients, while a closed formula for the binomial coefficients was obtained by the mathematician Levi ben Gershon. Now, this is Rabbi ben ibn Ezra. And then we are all familiar with the name of Pascal. The arithmetical triangle graphical diagram showing the relationship among the binomial coefficients was presented by the mathematicians in treatises dating as far as back as the 10th century, and that would eventually become known as the Pascal's triangle. Combinatorics reached Europe in the 13th century through the mathematicians Leonardo Fibonacci and Jordanus de Nemo. Now, Jordanus was the first person to arrange the binomial coefficients in triangular form, and simultaneously in the Middle East, that is in Persia and China, also this is done. And today, this triangle is known as the Pascal's triangle, although it was discovered long before Pascal came into, long before Pascal's time. This triangle of binomial coefficients was studied by Pascal, and he found many connections between this triangle, the coefficients in this triangle, and probability. Now, together with Leibniz, Pascal published the art combinatoria in 1966, and this was reprinted later. Now, Pascal and Leibniz are considered the founders of modern combinatorics. So that is a little bit about the history of combinatorics. Now we are going into this, begin our study of combinatorics with two basic principles of counting. Most problems in combinatorics can be broken down into simple subproblems, which reduce to one of these two principles. Now the first rule is this: if I can do one task in m ways and I can do a second task in n ways, and both these tasks cannot be done simultaneously, and I want to do either A or B. For instance, if I have one task A and I have a second task B, and I want to do either A or B, then I can do either A or B in m plus n ways. Now this rule can be extended to as many tasks as I want. So I can write this: if the ith task can be done in ni ways, and no two tasks can be done simultaneously, then doing any one task can be accomplished in n1 plus n2 plus n3 and so on up to nr ways. Now let me illustrate that with an example. A student wishes to take either a physics course or a chemistry course, but not both. Now suppose there are 4 physics courses and 3 chemistry courses, and I'm assuming that the student is eligible to take either of the courses. Then he can choose the course to take in 4 plus 3 or 7 ways. Now the second question I can ask is, in how many ways can we select one project given 3 lists containing 8, 12 and 10 projects? Now how do I find it? Again, I'm going to use the extended rule of sum, and so I get 8 plus 12 plus 10. I think that adds up to 30. Now, uh, now the next rule that I want to talk about is the rule of product. If a procedure can be broken down into 2 stages, and the first stage can be done in m ways, for each possibility of the first stage, the second stage can be done in n ways, then the procedure can be done in m into n ways. This principle can also be extended to as many stages as required. One minute, please. Okay. Sorry for the interruption. Now, the second rule that I want to talk about is the rule of product. If a procedure can be broken down into two stages, and the first stage can be done in m ways, for each possibility in the first stage, the second stage can be done in n ways, then the entire procedure can be done in m into n ways. Now, this principle can also be extended to as many stages as required. And so, I have the extended rule of product, which says that if a procedure can be broken down into arcs.
Excuse me, ma'am.
Yes.
Still, we have that sound difference.
Hello.
Sound disturbance. Hello, ma'am. Can you hear me?
Yeah.
Can you please stop that recording? If you are recording, we have
I'm not recording.
Okay, ma'am. Can you please adjust your mic to your lips?
No, the thing you asked.
Still, there is a sound problem.
Okay. Okay. Can you hear me?
But still, there is sound disturbance. I don't know.
Maybe I think it's raining here, so that may
Okay, ma'am. Okay, ma'am. You can continue now. Sorry, ma'am, for the disturbance.
Okay. What I'm saying is audible. Hello.
Yes, ma'am. Yes. Yes, ma'am.
Okay. Okay. Let me go back to the extended rule of product. If a procedure can be broken down into arc stages, and first I-1 stages, the ith stage can be done in ni ways for each possibility of the first I-1 stages. Then the procedure can be done in n1 into n2 up to nr ways. Now, as an example of this, I take this example. The memory in a small appliance like a microwave oven is divided into a large number of small parts called cells. Now, each location of cell has a unique address, which is a sequence of, say, 16 bits. Now, all of us know that a bit can hold either 0 or 1. And so we have a total of 2 into 2 into 2, 16 times. Why 2 into 2 into 2? Because for the first bit, I have two options, 0 and 1. For the second bit, again, I have two options, 0 and 1, and so on. For each of the 16 bits, I have two options. So therefore, totally, I have 2 into 2 into 2 into 2, 16 times, or 2 per 16 different memory locations. Now, one more example. Suppose I want to come from Kanjirapalli to, from Amalajodi to Universal Engineering College, which is in Thrissur. We are in Kanjirapalli. Now, one way of coming from Kanjirapalli to Thrissur, for example, suppose I have 5 routes from Kanjirapalli to Ernakulam and 7 routes from Ernakulam to Thrissur. Then I have a total of 5 into 7, which is 35 routes from Kanjirapalli to Thrissur through Ernakulam. Now, suppose in this example, there are 20 more routes which do not pass through Ernakulam. Then I can use the rule of sum there to say that there are 35 plus 20 different routes from Kanjarpalli to Thrissur. Linear arrangements of objects. Let me start again with an example. A certain email server uses case-sensitive alphanumeric passwords. Now I'd like to see how many passwords of 8 characters can be found. Now we have a total of 62 symbols, and since there are no restrictions, we can say that for each position I have 62 into 62 into 60, and for each position I have 62 options, and therefore I have totally 62 into 62 8 times, or 62 raised to 8 possible passwords of length 8. Now suppose I add a restriction that no symbol is to be repeated. Then once I have taken for the first symbol, I have 62 options. But when I come to the second position, one symbol has already been used, so I have only 61 options. And when I come to the third, I have only 60 options, and so on till we come to the last position where I have only 55 options. So totally the number of possible passwords is 62 into 61 up to 55. Now this is basically what I mean by an arrangement. This is how I find the number of arrangements. So let me define the factorial notation. A permutation of a set S of distinct elements is an ordered sequence that contains each element of S exactly once. Now finding the number of permutations of n elements is equal to arranging n elements in some order. That means I'm going to put it in some order. Hence, for the first position I can choose any one of the n elements. For the second position, I can choose only from n minus 1 elements, and so on, till I come to the last position, then position where I have only one option. So therefore, the total number of permutations n into n minus 1 into n minus 2 and so on up to 1, which I denote by n factorial. Now let me illustrate that with an example. Consider the set ABC. Now what are the possible permutations here? I can have ABC itself, then I can have ACB, I can have BAC, BCA, CA. 6 different arrangements of these 3 symbols. Now next, so far we were taking the entire set and rearranging it in some other order. Next time we take only a subset of the set and I'm going to arrange them in some order. So an ordered arrangement of R distinct elements of S is called an R permutation of S. The number of R permutations of a set with n different elements is denoted by P and R. Now using the rule of product, number of R permutations of a set with n elements is given by P and R is equal to n into n minus 1 and so on up to n minus R plus 1. That means I have R elements starting from n and decreasing, each element decreases by 1. So ultimately it's going to be n factorial by n minus R factorial. For instance, if I take the number of 3 permutations of the word computer, I totally in computer I have 8 symbols and I'm taking 3 permutations here. So 8 factorial by 8 minus 3 factorial, which gives me 8 into 76 or 336. Now, the important thing to remember here is when we talk about a permutation, we are talking about a range. We're going to look at right now is what is called a combination. Now, the difference between a combination and a permutation is that in a permutation, the arrangement is very, very important. Whereas in a combination, it's not. I'm just looking at them at that ordered arrangement. So that is the key thing. This is one place where many students get confused whether they have to take a permutation or whether they have to take a combination for a particular problem. So the basic difference between a permutation and a combination is that in a permutation the arrangement is very important, whereas in a combination it is not important. We are not bothered about the arrangement. Definition: an R combination of elements of a set is an unordered selection of R elements from the set. Thus, an R combination is simply a subset of the set with R elements. For instance, suppose I take this set 1, 2, 3, 4. Then 1, 3, 4 is a 3 combination from S. Now, note that 4, 1, 3 and 1, 3, 4 is exactly the same, because when I'm taking it as a combination, the order in which the elements are listed does not matter at all. But if I was taking it as a permutation, I would have said that 834 is different from 413. This is what I mean. This is the basic difference between a permutation and a combination. The number of R combinations of the set with n distinct elements is denoted by CNR. Note also that CNR is, we use this notation for the number of combinations, NCR. Since each R combination of a set with n elements corresponds to R permutations of the n elements, it is given by the number of R combinations is given by PNR by R factorial, and in other words, it's equal to n factorial divided by R factorial into n minus R factorial. Now again, let me illustrate with an example. A group of 30 persons have been trained as astronauts to go on the first mission to Mars. How many ways are there to select a crew of 6 people to go on this mission? Assuming that all crew members have the same job. Now, the solution for that question is the number of ways to select a crew of 6 from the pool of 30 people is the number of 6 combinations of a set with 30 elements, because the order in which these people are chosen does not matter. Now, please note, suppose I say I had not said that all crew members have the same job. That is, suppose I have a captain and each member of the crew has a particular job, has a distinct job. Then what I would have wanted is not a combination. I would have looked for a permutation. Okay. So this is the basic difference. So the number that I want is this 30 C6, which I can simplify, and I get this value. Now one more example. Suppose I have 9 faculty members in the mathematics department. How many ways can I select a committee to develop a discrete math course? If the committee should consist of 3 members from the maths department and 4 from the computer science maths faculty, I have 9 people, and out of that I need to choose 3, and therefore I can choose them in 9C3 ways. Again, from the computer science department, I have 11 people, of which I need to choose 4. So I can choose them in 11C4 ways. So totally I can use my product rule and say that the total number of such committees, total number of possible committees is Number of ways of selecting this committee is 9C3 to 11C4, which I can simplify and I get 27,720. One more example. Suppose I want to count the number of paths in the xy plane from the point 11 to the point 43, where each path is made up of individual steps going 1 unit to the right or 1 unit upwards. Now this is equal to the number of combinations of 3 arcs and 2 views. And so basically what I want here is I have 5 positions. Okay, I have to write a sequence of 5 positions. In each position, I think there are some technical issues, so please wait for a minute.
Dear participants, there is a technical issue. Please wait 2 minutes.
Hello. Hello. Am I audible? Hello. Am I audible?
Yes, ma'am.
Okay.
Ma'am,
Do you want me to go back and
please open your video. Videos.
okay, you want me to move the video? Okay. Okay.
There is a noise issue, is there? So continue. No problem.
Okay, but do you want me to go back?
Okay. Okay, ma'am.
I'll go back. I'll go back to some extent. Let me see. Yes. Okay. I'm just going to repeat this problem once again. Suppose I have 9 faculty members in the mathematics department and I have 11 in the computer science department. Now I want to frame a discrete math syllabus. So how many ways can I select a committee to frame the syllabus. Here the committee should consist of 3 faculty members from the Maths department and 4 from the Computer Science department. According to the product rule, we have to find the number of ways we can choose the mathematics faculty and the number of ways we can choose the computer science faculty and multiply them. So first let me see how many different ways I can choose the mathematics faculty. Now I have totally 9 mathematics faculty and I need to choose 3 of them. So that can be chosen in 9C3 ways. Similarly, the computer science faculty, there are 11 of them, of which I need to choose 4. So therefore, I can choose them in 11C4 ways, and totally, I can, according to the product rule, I have 9C3 into 11C4 ways of choosing this committee. And that turns out to be 27,720 after all our simplification. Now the next problem that I want to look at is this. I want to determine the number of parts in the xy plane from the point 1, 1 to 4, 3. And I'm going to assume that each path is made up of individual steps going either 1 unit to the right or 1 unit upwards. Now this is equivalent to finding the number of combinations of 3 R's and 2 U's. Okay, in other words, I need to place 5 symbols in a row. 3 of them are R's and 2 are U's. Now that is equivalent to just choosing 3 of the 5 positions for the R's and allocating them to the R's, and the other 2 positions I'm going to fill with U's. So therefore, how many ways can I do it? 5C3 ways. And the total number of such paths is 5C3, which is equal to 5 factorial by 2 factorial into 3 factorial, which is 10. Now, so far, when we talked about combinations, we assume that we are not repeating any elements. Now, in case we are going to allow repetitions in the combinations, then the number of combinations is given by n plus r minus 1 CR. For example, now I have a shop which offers 20 different types of toys, and I'm assuming that there's no limitation on the number of toys available of each kind. So suppose I want to buy 12 toys. I want to buy toys for 12 different children. Now how many different ways can I buy it? It's not necessary that I choose different toys for each child. In some cases I may want the same toy for 2 different children. So how many ways can I do that? I can choose it in 20 plus 12 minus 1, C12 ways, which when I simplify, I get this number. It's a big number, so 141, 120, 525. Okay. Now, the next question, it doesn't seem to be anything connected with what we've been talking so far. Here, we are trying to find the number of integer solutions to this equation, x1 plus x2 plus x3 plus x4 equal to 7. Now, how do I solve this? When I first look at it, it doesn't seem to have anything in common with this concept of combinations with repetitions. But this is a typical example of an application of this formula. Now, this problem is equal to distributing 7 chocolates. Suppose I have 7 chocolates, and I distribute these 7 chocolates to 4 children. That is, I'm going to give x1 chocolates to the first child, x2 to the second child, x3 to the third child, and x4 to the fourth child. And the total should be equal to 7. Okay. So when you interpret the problem in this way, I find that this problem is equal to distributing 7 chocolates to 4 children, and hence I have a total of 7 plus 4 minus 1 C4, or when I simplify that I get 120 solutions. One more problem. We would like to distribute 7 bananas and 6 oranges among 4 children in such a way that each child gets at least 1 banana. Again, this doesn't sound very easy to do. How do I count the number of ways? Now, what I would like to do first is I have a condition that each child will get at least 1 banana. So I take the bananas first and I start distributing them. I give 1 banana to each child. Okay. Then once I've given 1 banana to each child, how many bananas do I have left? I've started with 7 bananas. I've given 1 banana to each child. So there are 4 children. So we have 3 bananas left. So basically now the problem is in how many ways can I distribute 3 objects among 4 children. Okay, 3 bananas to 4 children. And that, according to our formula for combinations with repetitions, is given by 3 plus 4 minus 1 C4, and that is 20 ways. Now, once I have distributed the bananas, I take the oranges and do the same thing with them. Here, there's no restriction that each child should get at least 1 orange. So I'm going to directly distribute the 6 oranges to the 4 children. And therefore, I have 6 plus 4 minus 1, C4, which is 84 ways. Now, both these things I have to distribute both the bananas and the oranges. So, there are 20 ways of distributing the bananas, and there are 84 ways of distributing the oranges. So totally I have 20 into 84, or 1680 different ways in which the fruit can be distributed according to our given conditions. Now we come to another problem. This looks a lot like the problem we did a little time back. How many non-negative integer solutions are there to the inequality x1 plus x2 up to x6 less than 10? Now, when you look at this problem, you'll say, oh, this is a repetition of the problem we saw it some time back, that x1 plus x2 plus x3 plus x4 is equal to something. Okay, so my obvious way of solving this would be take the right hand side as k, take it as x1 plus x2 plus x3 up to x6 equal to k for each value starting from 1 and ending with k minus 1. Of course, it is possible for me to do that, but then the problem is that when k becomes large, here 10 is manageable, but what happens if instead of 10, my right hand side was 1000? Then the problem becomes very tedious. And so that's not a very efficient way of doing this problem. Okay. So this is intuitively this is the first thing that I will try to do. Okay. So let me see if I can do it in some other way. Now instead we try to find the number of non-negative integer solutions of x1 plus, I add one more variable x7. So x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7 equal to 10. Now I know that xi is greater than equal to 0. And suppose I say that x7 is not 0, if x7 is anything other than 0, then obviously x1 to x6 should be strictly less than 10. So basically, the solution of that first inequality, the number of solutions for that first inequality will be exactly the same as the number of solutions to this equation that I've written. Okay, but still I'm not able to solve it directly because I have the formula I developed earlier said that all my variables should be greater than 0. There was no other condition greater than or equal to 0. Here I have x7 is strictly greater than 0. So there should be some way to take care of that also. Now what I do is this. I take y1 as x1 itself, y2 as x2 itself, and so on till I get y6 equal to x6. And y7 alone I take as x sub x7 minus 1. And then when I put that into this equation, I get y1 plus y2 plus y3 plus y4 up to y7 is equal to 9. And so I get, now I've got, this equation is exactly in the form that I looked at earlier. And so I can directly give the answer. The number of solutions for this is 7 plus 9 minus 1, C9. This is a summary of what we've been saying so far about permutations and combinations. Next, we come to the binomial theorem. Suppose x and y are variables, and suppose n is a non-negative integer. Then the x plus y raised to n can be expanded in terms of the binomial coefficient according to this formula. nc0 x raised to n plus nc1 x raised to n minus 1 y plus nc2 x raised to n minus 2 y squared, and so on till we reach ncn y raised to n. Now, because this symbol NCR appears in the binomial theorem, it's also referred to as the binomial coefficient. Now, these are some very simple problems associated with binomial coefficients. What is the coefficient of x power 12, y power 13, and the expansion of x plus y raised to 25? It's a direct problem. From the binomial theorem, this coefficient is given by 25c13, which is 25 into 13 factorial by 12 factorial, which I can simplify. Now again, let me ask, what is the coefficient of x power 12, y power 13, and the expansion of 2x minus 3y raised to 25? This again is fairly simple, but it's slightly more complicated than the previous problem. According to the binomial theorem, we have 2x plus 3y raised to 25. I can write as 2x plus minus 3y raised to 25. And now I apply my binomial theorem. And so when I simplify that, I have a 2 here, 2 raised to 25 minus j. I have a minus 3 raised to j here. So if x should be 12, this 25 minus j should be equal to 12, and therefore j should be equal to 13. Okay, so substituting that here, I get the 25 C13 into 2 raised to 12 into minus 3 raised to 13, which I can simplify. Now I have two simple results which come as corollaries to this result. Suppose n is a non-negative integer, then the summation of all these binomial coefficients from k equal to 0 to n, nck is equal to 2 raised to n. Now the proof is very simple. Using the binomial theorem, I just put x equal to 1 and y equal to 1, and I get this result directly. One more easy result. If n is a positive integer, then the sum of minus 1 raised to k nck is equal to 0. When here what I do is I put x equal to minus 1 and y equal to 1 in the binomial theorem. And again, simplifying this, I get this expression. So I get that equal to 0. And so we get a result that the sum of nc0, nc2, nc4, and so on is the same as nc1, nc3, nc5, and so on. Next, we have what is called the multinomial theorem. For positive integers n and t, the coefficient of x raised to n1, x raised to n2, up to x raised to n3, in the expansion of x1 plus x2 plus x3 up to xt raised to n is given by n factorial divided by n1 factorial, n2 factorial, nt factorial, where each ni is an integer, where and ni is lies between 0 and n for all I. And when I add up all the values of ni, I get n itself. Now again a simple example. What is the coefficient of a cubed c squared term in the expansion of a plus 2b plus 3c raised to 5? Now we see here that all that I need to do here is equate the coefficients. Clearly n is 5, x1 is a, x2 is 2b, x3 is 3c, n1 is 3, n2 is 0, and n3 is 2. So my required term is 5 factorial by 3 factorial into 0 factorial by 2 factorial into 3 squared, which I can simplify as 90. Now the next topic that we are going to look at is using Venn diagrams for combinatorial arguments. The number of elements in the union of two sets A and B is the number of elements of the set A and B in both the sets minus the number of elements in their intersection. You can see that here. This, when I take the union of this portion is repeated. This A intersection B is repeated twice, and so I need to count it only once. So when I add the size of A and the size of B, I need to subtract the size of A intersection B. Let me again look at a simple example here. Find the number of multiples of 2 or 3 in the range 1 to 20. Now let me list them out. The multiples of 2 are 2, 4, 6, 8, 10, 12, and so on. We go on up to 18 and 20, which is a total of 10 numbers. Again, when I look at the multiple of 3, I have 3, 6, 9, 15, and 18. So I have totally 6 numbers. Now the answer is not 10 plus 6, 16, because I find that 3 numbers 6, 12, and 18 appear in both the classes. So I need to subtract these 3 elements, and so at least from one of the lists I should it should be excluded, and therefore the answer is 16 minus 3 or 13. Let me look at the next problem. In a discrete maths class, every student is a major in either computer science or maths or both. The number of students having computer science as a major is 25. The number of students having mathematics as a major is 13. And the number of students majoring in both computer science and mathematics is 8. This is something that happens in other universities. It doesn't normally happen in India, but abroad this is very common. You can have more than one major. Now the question is, how many students are there in this class? Now the solution is this. Suppose I take A to be the set of students in the class majoring in computer science, B is a set of students majoring in mathematics. Then A intersection B is a set of students who are joint mathematics and computer science majors. Now because I know that every student is in the class majoring either in computer science or mathematics, it follows that the number of students in the class is A union B. The size is the size of A union B. And I know that A union, size of A union B is size of A plus size of B minus A intersection B. And therefore, this is equal to 25 plus 13 minus 8. When I simplify, I get 30 students. This is the number of students in that class. A little more complicated example. Suppose I want to find the number of integers not exceeding 1000 which are divisible by either 7 or 11. Now, how many, let me take A to be the elements from um, between 0 and 1000 which are divisible by 7. Now, how many elements are divisible by 7? How do I find that? Basically, what I do is I divide 1000 by 7 and I take the flow function. I hope all of you are familiar with the flow function. The flow function just takes the integer just below that number. For instance, if I take uh, 10 divided by 3, I get 3 because when 10, the flow function of 10 by 3 is 3. Because when I actually divide 10 by 3, I get 3.33. I take the number immediately below that. Of course, if I'm going to divide 10 by 2, I get 5, in which case I don't need to do anything. So if it is an integer, I keep it as it is. If it's not an integer, I take the number immediately less than that. So, and as I said earlier, I define A as a set of elements or set of numbers which are divisible by 7 between 0 and 1000, and B is a set of numbers which are divisible by 11. Now I know that A union B is a set of elements, set of numbers which are divisible by either 7 or 11. And A intersection B is a set of numbers which are divisible by both 7 and 11. Therefore, number of elements in A is flow function of 1000 by 7, and number of elements in B is flow function of 1000 by 11. Since 7 and 11 are relatively prime, that means they don't have any common divisors. If a number is divisible by both 7 and 11, then I can say that that number is also divisible by 7 into 11. So there are 1000 flow function of 1000 by 7 to 11 positive integers not exceeding 1000 which are divisible by both 7 and 11. Now let me put all this back into the equation and so I get the required number is size of A union B, which is size of A plus size of B minus the size of A intersection B. I've estimated each of these, I've actually evaluated each of these separately. So when I add all that, when I substitute all this in that formula, I get total as 220. Now we come to the next result, which is called the principle of inclusion and exclusion. If the membership of two sets A and B are defined in terms of the condition C1, C1 and C2, and if n of C1 is the size of A, n of C2 is the size of B, and n is the cardinality of the universal set in consideration, we find the number of elements satisfying either of these conditions given by n of C1 plus n of C2 minus n of C1, C2. Now this is simply what we said in the previous few slides. Okay, I've just written it in a different way. Moreover, the number of those not satisfying either condition is n of C1 bar C2 bar, which is n minus n of C1 plus n of C2 plus n of C1 C2. So this picture depicts what I was saying just now. Now let me extend this to T conditions. Suppose I have a set S with size is equal to capital N, and suppose I have T conditions C1, C2, C3 up to Ct. Now each of these conditions is satisfied by some elements of S. Now I'd like to find the number of elements which satisfy none of the conditions C1, C2 up to Ct. So what I need is n of C1 bar, C2 bar, C3 bar up to Ct bar. Now, it can be proved that the expression for that is n minus sum of n of C1 plus n of C2 up to n of Ct plus n the number of elements which satisfy conditions C1 and C2, conditions C1 and C3, and so on. I think that is, I take all combinations with which I take the number of all those elements which satisfy two of the conditions. And then in the next step, I take all those elements which satisfy three conditions, and so on. Now, to simplify our notation, we write n bar is n of C1, C2, C1 bar, C2 bar up to Ct bar, and hence we have S naught. And we also use this notation. I write S naught as n, S1 as n of C1 plus n of C2 up to n of C2, sorry, up to n of Ct, and therefore when I similarly I can define S2 as the number of elements which can satisfy two conditions, that is C1 C2 or C1 C3 or C1 Ct or C2 C3 and so on up to Ct minus 1 Ct. But till I ultimately reach St as the number of elements which satisfy all the conditions C1 C2 up to Ct. Or in general, Sk is the number of conditions which satisfy exactly k of the t conditions. And this summation is taken over all possible combinations of k of the t conditions. Then I get n bar is equal to S naught minus S1 plus S2 minus S3 up to minus 1 raised to t St. Again, let me illustrate what I've been saying with an example. I want to find the number of positive integers n which lie between 1 and 100 and which are not divisible by 2, 3 or 5. Now here in this case S is 1, the set 1, 2, 3 and so on up to 100 and capital N is 100. Now I define the three conditions C1, C2, C3 as divisibility by 2, by divisibility by 3 and divisible by 3 by 5. Then I know that the number of those integers which are divisible by 2 is 100 by 2, which is 50. Those divisible by 3 is 100, floor function of 100 by 3, which is 33. Those divisible by 5 is 100 by 5, floor function of that, which is 20. Then I have C1, C2. I want those numbers, integers, which are divisible by both 2 and 3. So that is 100 by 2 into 3 and flow function of that, which I get to be 16. N of C1, C3 is 100 by 2 into 5, which is 10. N of C2, C3 is 100 by 3 into 15, which is 6. And N of C1, C2, C3 is 100 by 2 into 3 into 5, which is 3. Now applying the principle of inclusion and exclusion, we get 100 minus 50 plus 33 plus 20 plus 16 plus 10 plus 6 minus 3 equal to 26. Now, a derangement is a permutation in which none of the objects appear in their original place. For example, if I take the elements 1, 2 and 3, the only possible derangements are 2, 3, 1 or 3, 1, 2. Anything else, at least one of the elements will be in its original position. Now we can use the theory of inclusion-exclusion to find the number of derangements of a set by taking Ci as a condition that the ith element is in the right position. Then the number of derangements of a set of size n is given by dn, which is n of C1, C1 bar, C2 bar, Cn bar, which is equal to n factorial. N factorial is the total number of possible arrangements of n elements. So I have n factorial minus nc1 into n minus 1 factorial, nc2 into n minus 2 factorial, and so on till I reach Cn. And it can be shown that this number is approximately n factorial by e. Now we come to the pigeonhole principle. Suppose this is what the pigeonhole principle says. If I have m pigeons and they occupy n pigeonholes and m is greater than n, then there's at least one pigeonhole with two or more pigeons roosting in it. Now again, let's look at a few very simple examples. Among any group of 367 people, there must be at least two who have the same birthday. Because in a year I have only 366, maximum I can have only 366 possible birthdays, even if I count a leap year. So when I take the 367th person, then obviously at least two people will have the same birthday. Again, if I take any group of 27 English words, there must be at least two which begin with the same letter, since I have only 26 letters in the English alphabet. These are all very obvious applications of the pigeonhole principle. We'll come to a few more complicated ones a little later. Again, we would like to check how many students must be in a class to guarantee that at least two students receive the same score in the final exam. If the exam is graded on a scale from 0 to 100 points. Now, what are the different marks that you can get? 0, 1, 2, 3, up to 100. So, there are how many different possibilities? I have 101 possibilities. 0, 1, 2, 3, up to 100. Okay. And therefore, if I want to make sure that at least two students receive the same score, then there should be one more student than the number of possible marks. And so, if I have 102 students, then there must be at least two students with the same score. Now this is slightly more complicated. Show that it's not so obvious that this is an application of the pigeonhole principle. Suppose I take an equilateral triangle with side 2. I want to show that in whichever way I choose 5 points. Suppose I'm able to choose 5 points in this triangle. Now, whichever way I choose 5 points, there will be at least one pair whose distance is less than or equal to 1. Now, how do I do that? Now, the answer is this. I divide this triangle into 4 portions by joining the midpoints of the sides. And now, if I take 5 points, it's very clear that at least 2 of the points should lie within the same region. And one result we know is that any 2 points in an equilateral triangle, the maximum distance is the length of the sides, and the length of the sides of the small triangle is 1. And therefore, since there are at least 2 points which are within the same region, their distance has got to be less than or equal to 1. Some more examples. Now this is a little more complicated. A salesman sells at least one car every day for 100 consecutive days, and he sells a total of 150 cars. Now I need to show that there is a period of consecutive days during which he sold exactly 10 cars. Okay, so the solution for this problem is, suppose I take k as 1 to 100, and suppose ak is the number of cars sold on the kth day, and I take sk to be the sum of a1, a2 up to ak. Now I know that s1 is less than s2. S1 is the number of cars which is sold on the first day, S2 is the number of cars which he has sold on the first and second day. S3 is the number of cars he sold on the first, second, and third day. And remember, I told you that every day he sells at least one car. So therefore, all these are strict inequalities. Okay, and totally he's sold only 150 cars. Okay, so S100 is 150. That I know. Now, so I have from S1 to S100, I have 100 numbers lying between 1 and 150. Now again, so I have 100 integers there. Now I'm just going to take another set of 100 integers. That is, I'm going to take S1 plus 10, S2 plus 10, S3 plus 10, up to S10, S100 plus 10. Now this has got definitely to be less. Now S100 is, I know, 150. So S100 plus 10 is 150 plus 10, which is definitely less than 200. Okay. Now look at these two sets, S1, S2 up to S100, and S1 plus 10, S2 plus 10 up to S100 plus 10. S1 plus, okay. Now I have 200 numbers here. S1, S2 up to S100 is 1. There I have 100 numbers. S1 plus 10, S2 plus 10, S100 plus 10. Just look at them as numbers. Don't look at them, don't give them any other interpretations. This is where most people get confused. If I just look at them as integers, I have 200 numbers, and all these numbers lie between 1 and 1 and 199. In fact, they lie between 1 and 160. And no two of these numbers are equal. No two of the numbers Sk is equal, because we said here that the Sk's or these are strict inequalities, and each of these are also strict inequalities. And so no two of these numbers S1 to S100 are equal. No two of the numbers S1 to SL plus 10 are equal. And so we have, according to the pigeonhole principle, I have 100 plus 100, 200 numbers lying between 1 and 160. And therefore, some of these numbers definitely have got to be repeated. Let me assume that at least one is repeated. So suppose I have Sk is equal to SL plus 1. Why Sk is equal to SL plus 1? Because I said that none of the Sk's are repeated. None of the SL plus 10s are repeated. So the only possibility is that one element in the first set is equal to this one element in the second set. So Sk is equal to SL plus 10 for some K and L. Of course, one of them has got to be bigger than the other. So suppose I take K is greater than L. Then I have what is AL plus 1 plus AL plus 2 up to AK is equal to Sk minus SL. And Sk minus SL, according to our statement here, is equal to 10. So within that, from the L plus 1 today to the K today, I have the salesman has sold exactly 10 cars. Okay. So I have covered most of the portions of our syllabus right now. Now let me just look at a few more applicants. I said I listed a few applicants at the beginning of this lecture, but let me go through a few more. We are going to look at a few important applications. Number one, communication networks, cryptography, and network security. Now, permutations are frequently used in communication networks and parallel and distributed systems. Now, when I want to route different permutations on a network for performance evaluation, it's a common problem in these fields. And many communication networks require secure transfer of information. Now, this drives development in cryptography and network security. This area especially has become very significant nowadays because of the increased use of internet information transfers. Now, the encryption process involves manipulations of sequences of codes such as digits, characters, and words. Hence, they are closely related to combinatorics, possibly with intelligent encryption process. For example, one common type of encryption process is interchanging or permuting parts of a sequence. Next, permutation is the fast Fourier transform employed in speech encryption. Now, the next area that we want to talk about is computer architecture. Design of computer chips involves consideration of possible permutation of input to output pins. Field programmable interconnection chips provide use of programmable interconnection for a desired permutation. Arrangement of logic gates is a basic element for computer architecture design. Next, we look at computational molecular biology or bioinformatics. This is an area of, with a lot of interest nowadays, especially with the coronavirus research going on. People have been trying to make use of computational molecular biology to find some sort of a drug which will help in the cure of this disease. This field involves many types of combinatorial and sequencing problems such as atoms, molecules, DNA, genes, and proteins. One-dimensional sequencing problems are essentially permutation problems with certain constraints. Next, we look at languages. Now we have two types of languages: natural languages, that is the languages that we normally speak like English, Malayalam, and so on, and computer languages. Both of these are closely related to combinatorics. This is because the components of these languages, such as sentences, paragraphs, programs, and blocks, are arrangements of smaller elements such as words, characters, and atoms. For example, a string searching algorithm may rely on combinatorics of words and characters. Direct applications of these can include word processing and databases. Another important application area is performance analysis of these string searching algorithms. Now, next we have the study of computability. Now, what is computability? It is the study of what can be computed and how it is accomplished. Now, this draws heavily on combinatorics, especially we use the pigeonhole principle here to prove that certain problems you cannot find a solution. It's not that the solution has not been found so far. It can be actually proved that certain problems can never you will never be able to find a solution. Next, we come to what is called pattern analysis. In a broad sense, all the areas that we talked about earlier are special cases of pattern analysis. For instance, molecular biology studies patterns of atoms, molecules, and DNA, while languages treat patterns of sentences, words, and strings. Now, you can have many other forms of patterns, for instance, visual images, acoustic signals, and other physical quantities such as electrical, pressure, temperature, etc., which appear in engineering problems. Patterns can also be abstract without any associated physical meaning. These patterns can be represented in various ways such as digital, analog, and other units. Some of these types of patterns can be associated with combinatorics. There's been an extensive research on combinatorial pattern matching. Computer music can be a specialized application domain of combinatorics of acoustic signals. Now, scientific discovery. For certain types of knowledge discovery problems, generation of combinatorial sequences may be necessary in the process of yielding candidate solutions. For example, we may want to have a sequence of possible chemical or biological reactions and their formations. In each step of the sequence, we may generate combinatorial sequences of chemical or biological radicals, bases, acids, and molecular components as candidate solutions, and then we choose the most likely ones under certain rules and constraints. Again, mathematics, especially graph theory and number theory, generate combinatorial sequences as candidate solutions. The next application talks about databases and data mining. Now, queries in databases are multiple join operations, which are permutations of the constituent join operations. Data mining or knowledge discovery in databases is a relatively new field that aims at distilling useful information, often from large databases. In this area, the number of techniques have been developed, mostly using symbolic artificial intelligence, which can manipulate combinatorial sequences, patterns, or information elements. Non-symbolic knowledge discovery techniques such as genetic algorithms, genetic programming, also deal with solutions in the form of sequences of bits, digits, characters, and sometimes with program elements. Neural networks. This is another domain of non-symbolic artificial intelligence, sometimes deal with combinatorial patterns. Knowledge discovery techniques under uncertainty, such as Bayesian networks, Dempster-Shafer theory, fuzzy logic, and rough set theory, may have combinatorial solutions. Next, we talk about simulation. Permutation and combination can be used for simulations in many areas. Permutations representing various genotype-phenotype associations are employed in genetic simulations. Other areas which employ permutations combinations for simulations include networks, cryptography, database, and operations research. Now, speaking about operations research, let's go a little deeper into that. Many optimization problems in operations research involve combinatorics. The job scheduling problem is essentially a sequential problem to determine the order of jobs to be processed in an effort to minimize the total time, cost, etc. Here, the jobs can be in a computer system, network, or a processing plant. Now, the traveling salesman problem tries to find the order of cities to be visited in order to minimize the total distance. Now, graph theory. Now, graph theory is one of the topics of this faculty development program, and I'm sure most of our other resource persons are going to talk a lot about it. I'm not going to say much, except that I just want to emphasize the importance of graph theory and its relationship with combinatorics. Combinatorics is crucial to graph theory. Graph theory deals with graphs or representations of objects in space. Graphs are used in geometry, computer science, and other fields to model the relationship between objects. In computer science, for instance, graphs are typically used to model computer networks, computational flow, and the structure of links within websites. Now, what is the link between combinatorics and graphs? Combinatorics is used to study the enumeration of graphs. That is, I want to count the number of different possible graphs which can be used for a certain application or a model. The shortest path problem of a graph is to determine a sequence of edges, the total length of which is minimum. Sometimes these problems are computationally difficult, that is NP complete or NP hard. In other words, it simply means that the problem is not easy to be solved, and therefore it requires extensive research. Lastly, we're going to security. This is a very specialized problem domain which came with a national major challenge after the 9/11 bombings. To confront, especially in the US, to confront this challenge, many intelligent computing techniques have been applied. including intelligent pattern analysis of human faces, X-ray images, chemical components, data from a distributed network of wireless sensors, etc. Natural language processing and data mining techniques have been applied to sift through and monitor the tremendous accumulation of electronic data. So, since we know that combinatorics can be extensively applied to these intelligent computing techniques, there's a wide spectrum of potential for this issue. Specific examples include string searching algorithms and their performance analysis in communication data, pre and post analysis of combinatorial sequences of information elements, and combinatorial pattern matching. I think that's it. Thank you for patiently listening to me. And if there are any questions, I'm ready to answer that.
Now the presentation, thank you ma'am. Now the presentation is over. It is time to clarify your doubts and you can take some time and ask the question. Otherwise you can put your questions into the question box in your command panel, control panel. Also, I would like to request you to fill the feedback form that are available in the chat box. It will be available for 30 minutes only, so be fast. It will be considered as your attendance sheet. So audience, please ask the question. Ma'am, one more question is there. The questions from Anubhav Prasad. Can you please discuss NP problems?
NP problems. NP, it's a little difficult to discuss it right now because basically an NP problem is a problem which takes polynomial time, non-deterministic polynomial time for a Turing machine. Basically, the idea is when I have a computer algorithm, I need to analyze it. If I want to compare two different algorithms and say which one is better, there are two ways of doing it. One is I can test both these algorithms on a particular machine and say one of these machines is faster, one of these algorithms works faster, and the other algorithms work slower on a particular machine. But the problem with this approach is that when I look at different machines, I may get different kinds of results. And so that's not a very standard way of doing things. The other way of doing it is I actually try to estimate the amount of time that a particular algorithm will take in terms of the size of the input. If I want to write it as a function of if I want to take the time that the algorithm takes as a function of the input. Of course, when the input size increases, the program normally will take more time. But if I try to write it as a function of the time required to solve that particular problem, if that can be written as a function of the input size, I get what is called the complexity of that particular algorithm. And the problem is said to be NP. It's suppose it's said to be a polynomial problem if that the time taken for that computation is a polynomial in the size of the input. Now, usually when I talk about a system, we are talking about a deterministic system. That means after this, after one particular step, we go to the next step and so on. But when we talk about a non-deterministic system, for instance, a Turing machine, which you will be learning later, which the students will be learning later, there we can have what is called a non-deterministic system. And there, it's easier. It takes less time for a non-deterministic things to do system to do certain things, because the non-deterministic system will take the shortest possible sequence of steps, which will give me the result. And so, usually, a non-deterministic system will take less time than a deterministic system. And a problem is said to be in NP if it can be solved non-deterministically on what is called a Turing machine. It is said to be in P when it can be done in polynomial time on a deterministic system. And usually a problem which is considered one of the hardest in NP, I mean it takes the maximum time in NP, is said to be NP hard. We have to go into a lot of discussion about Turing machines and things like that to and analysis of algorithms to exactly define NP hard and NP complete problems. I hope that answers the question.
Okay, ma'am. The next question is from Dr. Sachin Kumar. Do you suggest any application on reliability analysis?
I don't know. I don't know of any such application possible, but I don't know of any such applications.
Ma'am, next question. In an example, you are used to floor function for both 7 and 11 as divided by 7 into 11, but there is a prime number. But here it is a prime number. My doubt it is a valid. My doubt it is valid only for primes or not. If no, then
no, it's not. It's not. It's not valid. No, it's valid for any number.
Solve for the other numbers.
No, it's not valid only. It's valid whether it's a prime number or not. Even if when it's not a flow function is not defined only for prime numbers. It's defined in general for all integers.
Ma'am, next question. Can you suggest any good book for combinatorics?
The best books that I can think of are the ones recommended in our syllabus: Grimaldi and Rosen.
Now, question is over. It is over, ma'am. Now the time is over, and it seems to we have to cover for all our topics. Thank you, ma'am. On the behalf of the Universal Engineering College, I would like to express our profound gratitude to presenter and the second day of our FDP, Dr. Lisa, ma'am. Thank you very much for each and everyone for making our FDP really successful one. We greatly appreciate the presentation you have to us. It is nothing short the incredibility and informative and interesting. Thank you, ma'am. Also, I express my sincere gratitude to our principal, Dr. Jos K. Jacob, sir, for your cooperation. I am glad to express our sincere thanks to our HOD, Dr. K. K. Narayan, sir, for your great support and coordination. Also, I am express the vote of thanks to all the staff members. Once again, thank you, everyone. We appreciate your effort and for being here. I would like to request you all to fill the feedback form that we have sent in the chat box, and I would like to remind that it will be available for 30 minutes. Now, I would like to remind you about for tomorrow FDP, Dr. Ramkumar PB on the topic partial ordering and lattices and its application. Thanks again for joining us today. Thank you, Lisa ma'am.
Thank you a lot. Again, I'd like to repeat, I thank the organizers for inviting me as an invited speaker here, as a resource person. And I'm very sorry about the network issue. There was a lot of delay because of the network issue. So I think I'm really sorry about that.
No problem, ma'am. It's very informative sessions for the K2 under scheme 2019 scheme and 2015 scheme. Thank you, ma'am.
Thank you, sir.
Okay, ma'am. Thank you.